Hey everyone, in this video we're going to go over section 5.2, the definite integral. In this section we're largely going to have a discussion about what an integral is, and in section 5.3 we're really going to get down to solving integrals. We're going to solve some today, but mostly a discussion. So let's begin with the definition of a definite integral. So if f is a function defined for a less than or equal to x less than or equal to b, and we divide the interval from a to b into n subintervals of equal width of delta x, we let x0 be equal to a, and then we have x1 and x2 all the way out to xn, which is equal to b, be the endpoints for these subintervals, and we let x1 star, x2 star, all the way out to xn star be any sample points in these subintervals. So xi star lies in the ith subinterval from x sub I minus 1 to x sub I. Cool. Then, the definite integral of f from a to b is this. This definition is just introducing this notation. This integral of this function dx is equal to the limit as n goes to infinity of the sums from I to n of f of x I star delta x. So we're really introducing this notation for what we were talking about last time, provided that this limit exists and gives the same value for all possible choices of sample points. If it does exist, we say that f is integrable. So let me get a new piece of paper and we'll dissect this a little bit. So dissecting what this means, we have this big curly symbol. That symbol is called an integral sign, and it's actually an elongated s, an s for sum, because this integral is the limit of the sums. So we have an integral sign. F of x is called the integrand. A and b are called the limits of integration. A is the lower limit of integration, b is the upper limit of integration, and dx indicates what the independent variable is. Finally, integration is the procedure of calculating an integral. So just some vocabulary, showing you some parts. I'm going to draw a picture of all of this and show you what it all means. So let me write something else. So geometrically, this is what we're talking about. So if we have this is read as the integral of negative 2x plus 4 dx is equal to 4. Or what it's getting at is we have this curve, and I know it's a straight line, but please allow me to call it a curve. We have this equation, this curve, and this is its graph. Integrals are talking about areas. What we have been doing is we've been creating boxes, and we've been approximating the area under the curve with a series of boxes. But what this notation is saying is the area. This integral sign tells us the area. So the area between the curve, negative 2x plus 4, so the area between that curve and the x-axis, that's the dx, between x is equal to 0 and x is equal to 2 is 4. And we can get that just from the picture. We get this triangle, it's got a base of 2, it's got a height of 4, and we know that the area of this triangle is base times height divided by 2, or 2 times 4 divided by 2, which is 4. So the area between this curve and the x-axis, and bound by x is equal to 0 and x is equal to 2, is equal to 4. But there's a thing about definite integrals. It gives us what is called a net area, in that the area above the x-axis will be returned as a positive value, and the area beneath the x-axis is going to be returned as a negative value. So, when we talk about the area between the curve negative 2x plus 4 and the x-axis between x is equal to 0 and x is equal to 3, well, we have 4 units of positive area up here, and we have 1/2 of a unit of negative area down here. If you think geometrically, or if you think graphically, and you draw some rectangles, it would make sense on why we're getting negative values, because we would get the height times a width plus a height times a width plus a height times a width. So we would get a negative value for the area down here. So that's just something to be aware of. For now, what we're going to be doing is we're going to be talking about net area or total area. Later, we're going to be breaking these functions up at their x-intercepts, and we'll get a total area using some absolute values. But for now, our integrals, it'll give a negative value for area if part of the function lies beneath the x-axis, and a positive value for the area if the function lies above the x-axis. So continuing on, if we have this function, and it's true for any function, I just provided one for an example. So if f of x is negative 2x plus 4, that means f of r would be negative 2r plus 4, and f of t would be negative 2t plus 4. So the integral from a to b of f of x dx is equal to the integral from a to b of f of r dr, which is equal to the integral from a to b of f of t dt. All these are equal because all we're really doing is relabeling this axis. This is the area between this curve and the x-axis. This is the area between this curve and the r-axis. And this is the area between this curve and the t-axis. All we're doing is changing the name for our independent variable. So all of these are exactly the same in the way you manipulate them, in the way you approach them. All we're doing is changing the name of our variable. And in that definition that I provided at the beginning of the video, this little chunk, the sum from I is equal to 1 to n of f of x sub I star delta x, we call those the Riemann sums, or the Riemannian sums. So you'll hear there'll be examples that we're doing when I'll say calculate the Riemann sums, and that's saying that, okay, for some value of n, approximate the area under the curve. And finally, not all functions are integrable. We have two theorems for now that are going to help us to know which ones we can integrate. So the first one, if f is continuous on a to b, or f has only a finite number of jump discontinuities, then f is integrable on the closed interval from a to b. That is, the definite integral, the integral from a to b of f of x dx exists. And so remember, integrals are limits. So that's why we're talking about an integral existing. Integrals are limits, so we use the same language here. And so what this is getting at is, if f is continuous, or only has a finite number of jump discontinuities, and it doesn't have to be a stair step, it's just a stair step is easy to draw, you can calculate the area under the curve. If there's an infinite number of these jump discontinuities, then you do not have an integrable function. And also, so if f is integrable on that closed interval, then the integration is equal to this sum. This at first to me didn't seem that powerful, but if you look at what this theorem provides, it provides us a method for knowing which functions we can take the integral of, a definite integral of, and this theorem kind of gives us the ability to perform that operation. We don't yet know how to calculate these in its current form, but this theorem allows us to revert these integrals, these questions about area, to something we can work with. Now once we get to 5.3, we're going to get away with using these sums. Math books typically build up to ideas, and so we're building up to an idea now. So our first example, express the limit as n goes to infinity of the sum from I is equal to 1 to n of xi cubed plus xi sine of xi delta x as an integral on the interval 0 to pi. So this first example is just getting us used to how we can jump between notation. This is from page 1, and it says that the limit as n goes to infinity of the sum from I is equal to 1 of n of f of x of I star delta x is this integral. So we get this limit of sums to be equal to the integral from a lower bound is 0, our upper bound is pi, of this function. We get x cubed plus x sine of x, all in parentheses, dx. So this is just converting between the two. In general, what you're going to do is the first thing, or not really the first thing, the three things you're going to have to do is you're going to replace that limit of a sum with an integral. Another thing you're going to do is you're going to replace xi's with x's, and the last thing you're going to replace delta x with a dx. And these go in both directions too. So if you're tasked with, say, going in this direction, you're going to replace an integral with a limit and a sum. You're going to replace x's with xi's, and you're going to replace dx's with delta x's. So our goal is to evaluate integrals. And for now, what we're going to be doing is we're going to be using that limit definition to evaluate some integrals. When we're using that limit definition, we're going to have to work with sums. So these three rules, if you will, they're going to be what we're going to use for now to evaluate these sums. The sum of the first n integers is n times n plus 1 divided by 2. That's like 1 plus 2 plus 3 plus up to some number n. The sum of the first integer squared, the first n integer squared, is n times n plus 1 times 2n plus 1 over 6. So that's like 1 squared plus 2 squared plus n squared. And the first n integers cubed, or at least their sum, is n times n plus 1 divided by 2, that quantity squared. Also, working with sums, so down here, c is just some plain old constant. So constants can be pulled in and out. The sum from I is equal to 1 of n of some constant is just c times n. This is where I meant to say constants can be pulled in and out. This sum only cares about i's, so this c isn't bearing on I, or it isn't dependent upon I should say, so we can pull constants that don't depend on this index up and out. And you can break sums up at addition and subtraction. The sum of the sum is equal to the sum of the sums, or the sum of the difference is equal to the sums of the difference. So we'll go forward using really these 6 rules in this section to evaluate definite integrals. So for our next example, we're going to evaluate the Riemann sums for f of x is equal to x cubed minus 6x by taking the sample points to be the right endpoints, and a to be 0, b to be 3, and n to be equal to 6. And then we're going to evaluate this integral going back to the limit of sums. So starting with with letter A, I should say. So if we're trying to calculate our, or if we're going to use our Riemann sums and we're going to use our right endpoints when n is equal to 6, we're really looking to calculate R6 from 5.1. So what that'll be is R6 is going to be f of x1 times delta x plus f of x2 times delta x plus f of x3 times delta x plus f of x4 times delta x plus f of x5 times delta x plus f of x6 times delta x. So we need a delta x. Delta x is going to be 3 minus 0 divided by 6, which equals 1/2. And we need to figure out what our right endpoints are. Well, if we're starting at 0, and the width of our interval is 1/2, we would have the subinterval 0 to 1/2, 1/2 to 1, 1 to 3/2, 3/2 to 2, 2 to 5/2, and then 5/2 to 3. For our right endpoints, we would take 1/2, 1, 3/2, 2, 5/2, 3. So R6 is going to be equal to f of 1/2 times 1/2 plus f of 1 times 1 half plus f of 3 halves times 1 half plus f of 4 halves, 2, times 1 half plus f of 5 halves times 1 half plus f of 3 times 1 half. And when you finally calculate f of these values and you multiply and add all together, we're going to get R6 to be about equal to negative 3.9375, which is fine. Our area is negative. What that means is that more of this function, by our approximation I should say, more of this function, more of x cubed minus 6x is beneath the x-axis than above over 0 to 3. So there's just more of this thing beneath the x-axis than there is above over this interval. Now let's actually evaluate this limit. So for part B, we're actually going to evaluate this integral. To evaluate this integral, for now, we're going to go back to this limit definition. The limit, as n goes off to infinity, of the sum from I is equal to 1 to n of f of x sub I times delta x. And so now we need to figure out some information. Like, first off, we need to discuss what delta x is. Well, delta x is going to be 3 minus 0 divided by n, or just 3 over n. And we need our x sub i's. X sub i's are equal to a plus I times delta x, which in this case is going to be equal to 0 plus I times 3 over n, which xi I'm going to write as 3I divided by n for now. So we can perform these substitutions into this limit. We get the limit as n goes off to infinity of the sum from I is equal to 1 to n of, we're going to get xi cubed minus 6 times xi times delta x, which is going to be 3 over n. Perfect. So let's further substitute. This is going to be equal, and I don't have space to go over here, so this is equal to the limit as n goes off to infinity of the sum from I is equal to 1 to n. We know what xi is. Xi is going to be 3I divided by n cubed minus 6 times 3I divided by n, all times 3 over n. So now we're going to simplify some. This is going to be equal to the limit as n goes off to infinity of the sum from I is equal to 1 to n of 3 times 3 times 3 gives us 27I cubed divided by n, minus 6 times 3 is 18I divided by n, and that's still times 3 over n, which distributing gives us the limit as n goes off to infinity of a sum I is equal to 1 to n of 27 times 3 is 81I cubed. Did you guys catch my mistake? When I cubed my numerator, I forgot to cube my denominator. So n times n cubed would give us an n to the 4th. And then from that, we're going to subtract 18 times 3 is 54. 54I divided by n squared. This I'm going to copy on the back. Perfect, so all I did was I copied this part over from the previous page. So now we're going to use our rule that says we can break up sums at addition and subtraction. So this is going to be equal to the limit as n goes off to infinity of, we're going to have the sum from I is equal to 1 to n of 81 I cubed over n to the fourth minus the sum from I is equal to 1 to n of 54i divided by n squared. We're still taking the limit, so we need these big parentheses around the outside. Now, the important, there's two variables here. Kind of there's two letters. I'll say that. We've got this n on top of the sum, and we've got this n, or this I on the bottom of the sum. We also have this n over here, but I'm not talking about that n over there. I'm talking about this n and that I, and this n and that I. You cannot, I'll say that, you cannot pull an I in front of this sum. You can pull anything that is not an I. So you can pull constants up and out, and you can pull this n up and out. By that I mean we can turn this into limit n goes off to infinity of 81 over n to the fourth times the sum from I is equal to 1 to n of I cubed minus 54 over n squared times the sum from I is equal to 1 to n of I. So the only thing this sum cares about is I. And this sum, they're the same sum, we just split them up. Only cares about I. So we could pull everything that wasn't an I out in front. So now we're going to go back to those rules that I had up a moment ago. This is going to be equal to the limit as n goes off to infinity of 81 over n to the fourth. The sum of the first n integers cubed is n times n plus 1 all over 2 squared minus 54 over n squared times, let me take a look at something. Yeah, times n plus 1 all over 2. And then let's put some parentheses there for good measure. Perfect. So just using those rules that I had a couple pages ago. Now let's simplify. This is equal to a limit as n goes off to infinity of 81 over n to the fourth times, this would give us n squared plus n squared. So we'll write that. We'll say n squared plus 1 all over 2 plus n squared minus 54 over n squared times n squared plus n all over 2 equals limit n goes off to infinity of 81 over n to the fourth times, that would give us n to the fourth plus 2n cubed plus n squared, all divided by 4, minus, we'll say 2 goes into 54 27 times, and we'll call that 27 over n squared times n squared plus n. Sorry, I was running out of space. So further simplifying, this is equal to the limit as n goes off to infinity of, we would get, so breaking it up term by term, distributing, this would give us 81 divided by 4, 81 divided by n to the fourth times n to the fourth divided by 4, plus we'd get 81 times 2, which is 162, n cubed divided by 4. Then n cubed divided by n to the fourth would put an n in the denominator there. And then plus we'd have 81 divided by 4n to the fourth. Minus This would give us 27. 27 divided by n squared times n squared would just give us a minus 27, and then minus a 27 divided by n. As we let n go to infinity, this term goes to 0, this term goes to 0, and this term goes to 0, and we're left with 81/4 minus 27, which is actually exactly equal to, not approximately, is equal to negative 6.75. So there was a lot to this problem. So, where did we begin? Really, we began here. So for part B, this is just using our definition and we're trying to figure out the pieces. Well, we need to figure out a delta x when we're going to be using that limit definition. Excuse me, when we're going to be using the limit definition, we don't get an exact value out for delta x because that width is supposed to go to 0. So we're going to have an n in our denominator. And we need to get some way of coming up with our xi's that has an n in it so we can iterate through. Once we get here, this is where the algebra begins. This limit you just write every time until pretty much the very last step. And you're going to try and algebraically manipulate this thing. You're going to really try and get it so you can use these definitions that I gave you a couple moments ago. I'm sorry, they're on the floor right now. I can't find them. We're trying to use the sums of i's, sums of I squareds, and sum of I cubed formulas. So once we factored out everything that had an n, and that's the big kind of trick here, is that you can pull all these n's in front of these sums, then we use the formulas that I provided you guys with, then you go through and evaluate the limit. So there's a lot to these problems. I didn't give you a lot on your homework, but there are some. Haha. And also, this number seems pretty far away from the number that we had calculated, that we had approximated. But let me write this down. For n and our right sums, when n is 40, we get negative 6.3998. When n is 100, we get negative 6.6130. When n is 500, we get negative 6.7229. When n is 1,000, we get negative 6.7365. When n is 5,000, we get negative 6.7473. So as n gets large, the value of our n is in fact converging to negative 6.75. It just would take an incredibly large amount of n's for us to get close to that value. So that's why we're going through and we're evaluating these definite integrals definitely. For our next example, we're going to set up an expression for the integral from 1 to 3 of e to the x dx as a limit of sums using your right endpoints. So we're going to use the definition that the integral from a to b of f of x dx is equal to the limit as n goes off to infinity of the sum from I is equal to 1 to n of f of xi delta x. So we already know what this f function is. This is going to be our e to the x. We need to figure out what our delta x is and figure out what our xi's are. So our delta x is going to be the difference of our endpoints, 3 minus 1, divided by n. That's going to be equal to 2 divided by n. You get n's when you're evaluating limits of sums, and you get numbers when you're evaluating definite integrals. So 2 to the n, and we need our xi's. So x0 is going to be our starting point. x1 is going to be equal to x0 plus delta x, or 1 plus 2 over n. x2 is going to be x1 plus delta x, which is going to be 1 plus 2 over n plus 2 over n, which gives us 1 plus 4 over n. And x3 is going to be x2 plus delta x, which is going to be 1 plus 4 over n plus 2 over n, which is 1 plus 6 over n. I went this far down to help us see the pattern. Xi is going to be 1 plus I times 2 over n, which I feel oddly compelled to write as 1 plus 2I over n. It just bothered me to have the I out front. Now we finally have all the pieces that we need. We get that the the integral from 1 to 3 of e to the x dx is going to be equal to the limit as n goes to infinity of the sum from I is equal to 1 to n of e. Now we would put our xi's here, 1 plus 2 to the I over n times our delta x, which is 2 over n. So this is just the setup. We won't go through and actually solve this one, but this is how we would set up. We went one way, I believe, for example 1, and now we're going backwards for example 3. So example 4, don't forget that integrals are talking about area. Every integral has a picture. If we want to evaluate the following integrals by interpreting each in terms of the area, that means we really want to graph these things. For a, the square root of 1 minus x squared, that is a quarter of our unit circle. Goes from the point 1, 0 up to 0, 1. And despite my drawing, is a perfect circle. If the area of a circle with radius of 1 is pi r squared, the area of a fourth of that circle is 1/4 of pi r squared, and our radius is 1. So, geometrically, we get that this thing is equal to 1/4 of pi. B is similar. It's got a trick to it, but very similar. X minus 1 kind of looks like this. We're at the point 0, negative 1. We cross at the point 1, 0. And then we go up to the point, that would be 3, 2. So, if we wanted to evaluate this, remember that above the x-axis we get a positive value for area, and beneath the x-axis we get a negative value for area. This triangle has a base of 2 and a height of 2. Base times height divided by 2 is 2. Now down here we've got a base of 1 and a height of 1. So down here we have an area of 1. So when we go to figure out the entire area, we're going to get 2 minus the area that lies beneath the x-axis, which is 1, or just equal to 1. I'm sorry. Base times height divided by 2, we have an area of 1/2. So we'd get 2 minus 1/2, which is 3/2. Sorry. Base times height, don't forget to divide by 2. So, really, we can interpret these geometrically. Don't get scared by an integral. They all have a geometric interpretation. You can draw a picture of any integral. And then calculating the area, you can always rely on things you know from geometry, since these are geometric problems. So, a refresher from last time, the midpoint rule, saying that this integral is approximately equal to this sum, where for our x sub i's, we're going to take the midpoint of the interval. It doesn't matter what sample point you take in an interval. We have special notation for right-hand rules and left-hand rules and midpoint rules, but it doesn't matter where in that interval you take a sample point, and it doesn't even have to be in the same spot, relatively the same spot in each sample point. But we'll do as we're instructed. We will use the midpoint rule with n is equal to 5 to approximate that integral. So, using the midpoint rule, well, we're going to need a delta x. A delta x in this case is going to be equal to b minus a divided by n. which would be b minus a, 2 minus 1 divided by n, which is 5, which is going to give us 1/5. And we need an x sub I. So we're going to start at 1, and then the end of our next interval is going to be 1.2. Then we're going to go 1.2 to 1.4. Then we're going to go 1.4 to 1.6. And then we're going to go 1.6 to 1.8. And then we're going to take 1.8 to 2.0. The midpoint of each of these intervals, 1.1, 1.3, 1.5, 1.7, 1.9. So we get the integral from 1 to 2 of 1 over x dx being approximately equal to f of 1.1 times 1/5 plus f of 1.3 times 1/5 plus f of 1.5 times 1/5 plus f of 1.7 times 1/5 plus f of 1.9 times 1/5. Once you evaluate that, you get this integral from 1 to 2 of 1 over x dx being approximately equal to 0.691908. So we're getting there. We're slowly working up to actually calculating these integrals. This was just a refresher on the midpoint rule. There is this formula for coming up with your x sub i's. I think of it more geometrically. I know that we're breaking up this number line from 1 to 2 into equal chunks, and I'm just picking the point in the middle. You don't have to use the formula. You can just kind of reason your way through it. So now we've got some properties of definite integrals. If we took the integral from a to b of just some constant c, that's equal to c times b minus a. Because remember, if we have some equation y is equal to c, that's just a horizontal line. And so the area underneath this horizontal line, well, that's this line segment times that line segment, or just the area of a rectangle. We can break integrals up at addition and subtraction. The integral from a to b of f of x plus g of x dx is equal to the integral from a to b of f of x dx plus the integral from a to b of g of x dx. Constants, which should feel normal by now, can be pulled in and out of things that aren't dependent upon them. This integral only cares about things with x's. This constant doesn't have an x in it, so it can be pulled out front. And this one, the integral from a to c of f of x dx plus the integral from c to b of f of x dx is equal to the integral from a to b of f of x dx. So the picture of this final one is, so the area between a and c underneath this curve plus the area between c and b is equal to the area from a to b plus equals. So this is the picture behind what this one is going through. You can effectively stair step or walk from limits of integration as long as you don't have any gaps. Okay, so we've got these four properties. We're going to do two examples. From last time, we're going to have to remember that the integral of x squared dx from x is equal to 0 to x is equal to 1 is equal to 1/3. So, for example 6, we're going to use properties of integration to evaluate this integral. Well, for now, what we're going to do, 0 to 1 of 4 plus 3x squared dx, let's break these up at addition and subtraction. 0, 1, 4 dx plus 0, 1, 3x squared dx. We're going to leave this one alone. Integral 0 to 1, 4 dx plus that constant we'll pull up and out. 3 times integral 0, 1 x squared dx. you need these dx's. Well, using properties from our previous page, this is going to be 4 times 1 minus 0 plus 3 times 1/3, which gives us 4 plus 1, or 5. There are 5 units underneath this curve and the x-axis between 0 and 1. Or, using that last, now, using this one, I want to give you an example. So, if we know that the integral from 0 to 10 of f of x dx is 17, and the integral from 0 to 8 of f of x dx is equal to 12, we want to find the integral from 8 to 10 of f of x dx. Well, the integral from 0 to 10 of f of x dx is equal to the integral from 0 to 8 of f of x dx plus the integral from 8 to 10 of f of x dx. We know the value of this integral, it's 17, is equal to the value of this integral, 12, plus the value of this integral, 8, 10 fx dx. Subtracting 12 to both sides, and we get that the integral from 8 to 10 of f of x dx is equal to 5. So these properties can be derived directly from the sum, and this one shouldn't be too hard to wrap your mind around if you keep this picture in mind. We don't have to break it down to the sums, but just the area from here to here plus the area from here to here is equal to the area from there to there. So now we have this comparison property of the integral. So if this function lives entirely above the x-axis, between x is equal to a and x is equal to b, then the integral is going to be bigger than or equal to 0. Say that again. If this thing is always above the x-axis, above or touching the x-axis, then that means there's nowhere that it drops beneath the x-axis. There's no way that negative is going to return, there's no way that integral is going to return a negative value. So, if your function is always above the x-axis or touching the x-axis over a certain interval, you know that your integral is going to be positive over that interval. Similarly, if we've got one function that lives above another function, that means the area underneath the first function is bigger than the area underneath the second function. If this is our first function and this is our second function, of course there's going to be more area underneath the one that's on top. It's further away from the x-axis. And so finally is, if we know that there is the smallest value of f of x, what its minimum value is and what its maximum value is, we can come up with bounds we can come up with bounds for the value of the integral. So if m is less than or equal to f of x, which is less than or equal to capital M, we have the integral of lowercase m dx is less than or equal to the integral of f of x, which is less than or equal to the integral of capital M dx. Well, using properties of integration, this says that little m times b minus a is less than or equal to the integral from b minus a of f of x dx, which is less than or equal to capital M times b minus a. Cool, so the last thing we're going to do today is we're going to use one of our previous properties to estimate the value of this integral, the integral from 0 to 1 of e to the negative x squared dx. So, we need to come up with a lower bound, and we need to come up with an upper bound. E to the negative x squared is always decreasing. How do I know that? If we take the derivative of e to the negative x squared, that's negative 2x e to the negative x squared. And over the interval 0 to 1, this thing is always a negative number, or is either 0 or a negative number. That tells us we are always decreasing. So if you have a function that is always decreasing, its max value is going to start, or its max value is its starting point, and its min value is its ending point. So that means our lowest value, lowercase m, is going to be equal to this function, where am I pointing? This function evaluated at its endpoint, e to the negative 1 squared, which is about 1 over 2.7. And our upper bound, our capital M, is going to occur at our starting point, which in this problem is 0. So we get e to the negative 0 squared, which is 1. So what this says is that the integral from 0 to 1 of e to the negative x squared dx is bounded from above by 1 times 1 minus 0, and bounded from below by 1 over 2.7 times 1 minus 0, or 1 over 2.7 is less than or equal to the integral from 0 to 1 of e to the negative x squared dx, which is less than or equal to 1. Perfect. So there's a lot to this section. It's mostly just developing theory. We're really going to solve these integrals in the next section, but for now, we're just building up some ideas. To practice, for your homework, go off and do 17 through 25 odd, and 35 through 39 odd. And these are due the following Friday on the last day of school. Send me an email if you guys have any questions, and I'll talk to you next time.